So let's talk about acceleration in fluid mechanics. So back when we were in physics, we tracked particles. And for a particle, we rode on a particle here. And it had a velocity at time 1. And maybe at time 2, it has a different velocity. Okay, so for that kind of Lagrangian analysis, our acceleration was just dv dt, if you remember from physics, and that's because v was only varying with time. Okay, but now that we're in fluids, we're going to do control volumes, or Eulerian analysis, and for that, we are going to look at various positions in our control volume. And this v1, say, at this point 1, now is a function of position, x, y, z, and time, okay? So when we get an acceleration vector, we get an acceleration vector that covers this whole region. So it's all the particles that happen to be in that region at one time. So our acceleration vector is also going to be a function of x, y, z, and t, and it's going to be a little bit more complicated than it is for physics. So let's just do a little math here. So let's consider just any old arbitrary function, call it f, and it's just arbitrary. We're going to turn that into v later, but right now let's just some arbitrary function f, and we're going to take the derivative of it, just df, differential of it. And if you remember the chain rule for partial derivatives, since f is a function of x, y, z, and t, so that chain rule would be from your math methods course. What you're going to get is, well, df is the partial derivative of f with respect to time times dt plus the partial with respect to x. You're going to go through all the variables. dx plus the partial with respect to y, dy plus the partial with respect to z, dz. Okay, that's the chain rule for partial derivatives. Now take that df and let's divide by dt, basically. So we're going to end up with the derivative of f with respect to t, complete derivative. Okay, so if we do that, well, df dt times dt dt. Okay, well that is just 1, so that's going to drop out. Plus df dx dx dt plus df dy dy dt plus d, and those first ones are all partials and the second ones are ordinaries. So partial with respect to z times dz dt. Okay, so one thing to recognize here, dx dt, that is u. That's our u is our x component of our velocity vector, remember? dy dt is little v, dz dt, well, that's little w. So even though this is an arbitrary function, the velocities within your control volume are going to affect the derivative of whatever you're looking at in that control volume. So it's kind of like, mass flows in and flows out at entrances and exits. Velocity is going to affect no matter what you're looking for. Okay, so our df dt in the end here, some arbitrary function, we're going to use capital F or capital D's here, like that, in order to indicate, oh yeah, f is not just a function of t, it's a function of other stuff as well. So we use capitals for that, and then that's just going to equal df dt plus u df dx, all partials, plus v df dy plus w df dz. Okay, so that's a total or material or substantial derivative is the one with the big D's there that we usually use capital D to distinguish that. If we call, let's see, term A is your total derivative, call that A. B, local change with time due to unsteadiness, well, that's this. Okay, and then C is what's called the convective derivative. Okay, so that's the change in F, whatever it is, due to the fluid moving, and that's due to your velocity. So That would be term C as described down here. So you're going to end up with that u, v, and w in there no matter what f is. Okay, so let's say f was temperature. So if we wanted to, for example, we're standing out in the hot sun, couple ways that we can change our temperature. You can move to a cooler spot, that's your convective parts, or you can stand there and wait for it to get cooler, and that term would be like our dt term. Okay, so that's just an example. We're not going to use temperature. You would do temperature and heat transfer, but here we're going to use velocity. Okay, so for velocity, if we let f equal our velocity vector, then our dv dt is actually what our acceleration for a control ion is. Big D, the material derivative dt, which means it's not just the partial of v with respect to t, it's the partial of v with respect to t plus u times the partial with respect to x plus v times the partial of v with respect to y plus w times the partial of v with respect to z. All right. So, but if you look at this as a vector equation, so again, what you do is end up breaking it into components. So there's 4 here. If you divide it into your x, y, z components, now you're actually dealing with 12 terms there on the right-hand side. So a little bit more complicated. The way you break it into components is just instead of putting a v there with the vector, if for your x direction you use u. Okay, so it'd be your ax is equal to du dt plus u du dx plus v du dy. See what I'm doing? I'm putting in little u wherever I see v vector. W du dz. Okay, so that's our x component, and you could do the same thing for y and z components, only plug in for y component, you'd plug in little v in for big v vector. Okay, and same thing for z, plug in w. Okay, so let's just do an example of finding our acceleration for something where we already happen to know the velocities. Okay, so this example is a stagnation point, kind of like what we had on the front of our pitot probe or the front of our cylinder in the wind tunnel, right where that velocity hits head on, that wind hits head on. Okay, so let's say we got some measurements and we found that u, which is the x component of velocity, equals kx, and v equals minus ky, and w equals 0. It's a 2D flow, so there's nothing coming out of the page. We know we got derivatives going here. Let's just go ahead and take some derivatives here. Du dx. And partial just means, you treat everything that's not x as a constant. So that's equal to k. Dv dy is equal to minus k. Okay, and I don't have any other derivatives that are going to come into play here because there's no y's or z's or anything in u. So we are going to assume, since we're not given anything, there's no t's in here, we don't even have to assume, we can say that this has to be steady state. No t's. Okay, so we're going to find the acceleration vector at any point. Okay, so what we're going to do is say, okay, ax, we want to break it into components just like we did before. Well, that's du dt plus u du dx plus v du dy plus w du dz. Okay, and if we look at this, du dt, no t's in here. If we take the derivative with respect to t, 0. If we take the derivative with respect to x, okay, we're going to get k. So ax is equal to u, which is kx, plus, or times the derivative of u with respect to x. So that's times k. Okay, next term, plus v, which is minus ky, times du dy. Oops, that's 0. That's 0. Let's just erase that. We don't need that. And then w, well, w equals 0, so that's 0. So that's all we got for ax. Okay, so let's go ay. dv dt plus u dv dx plus v dv dy plus w dv dz. Okay, well, let's look at this. No t in there in v. Dv dx, well, that's 0 because there's no x in there. We do have a dv dy. W is still 0, so that's going to go away. Our ay then is just going to be left with, well, k, which is minus ky, and then dv dy, well, that was minus k, which equals k squared y. This, by the way, up here, the ax was k squared x. So that means our total velocity, or acceleration vector, is then k squared x I plus k squared yj. That's our answer. Okay, so whenever you're taking these derivatives, never substitute in numbers before you take the derivative. Okay, you always have to, if you're going to find something at some particular point, you do it after you've done all your derivatives and all your math. So if I wanted to find the acceleration at any x or y value, this is x and this is y, I now, after I'm done, could plug those in. Okay, so for instance, at the point 0, 1, I would plug in a 0 for x, and I would just get k squared j is my acceleration. Okay, just make sure that you do the math first, and then at the very end plug in your numbers. Never plug them in first. That's a common mistake. All right, so again, just a review on steady versus unsteady. Unsteady, by the way, also called transient. Steady flow, again, just like we did in thermo, if you watch your control volume, is anything changing? If anything is changing, it's unsteady. If it looks the same as it did 5 minutes ago, nothing is changing. And your steady state versus unsteady, the unsteady is going to be easier to solve. Okay, remember for steady flow, all terms with a ddt, or with a dt anywhere, can be canceled. All turbulent flow is unsteady, but we can solve it as steady on the average sometimes. All right, so stop here and do quiz questions 1 to 2.